Hello, my name is Almer Abatello, and I'm an undergraduate researcher working underneath Dr. Hassan Habib. I'm working on an in-house design and manufacture of a perfusion-based bioreactor for 3D cultures. You can see my SolidWorks assembly that I've created on the right. Here's my abstract. The world of cell cultures is changing as more and more biofabrication methods arise. As the field moves from 2D to 3D printing of viable scaffolds, the means to both seed and maintain cell proliferation becomes imperative. The use of perfusion bioreactors has shown success in both maintaining and encouraging proliferation of cells on a three-dimensional scaffold. Perfusion bioreactors maintain a flow of medium through the scaffold, mimicking the natural circulation of nutrients and hormones in vivo. The further replication of in vivo stimuli and conditions is the goal. Analyzing the performance of a bioreactor while operating is limited by the sealed nature of the system. To compensate for this, oxygen sensors will be implemented to track cell proliferation throughout the experiment. The dual medium tank design allows for medium replacement without pausing or ceasing perfusion flow, and to better simulate in vivo conditions, cyclical modulation of pressure will be attempted to simulate the natural pressure cues within the body. Here are some of the support components that I've designed. On the top left and top right, you can see the oxygen exchanges that I've made. The string is meant to represent the tubing that we will be using. The tubing in particular will be platinum cured silicone tubing. The first design, which is the one in the top left, was able to fit 1 meter of tubing into a 20 centimeter space. The one on the right, on the other hand, was able to fit 3 meters of tubing into the same 20 centimeter space, thus acting as the lungs of our system to better display the oxygen throughout it. So as the medium passes from the tanks into the exchange, it will be exposed to the gas permeable tubing, allowing for oxygen and CO2 to naturally balance out to the correct levels so that the cells can continue to consume their oxygen and continue to produce CO2, just like all of us do. At the bottom left and right, you can see the medium tanks themselves. On the left, our design was a little bit too bulky, a little bit too big. It didn't fit in with the rest of our bioreactor, so it was pared down so the dimensions fit better with the rest of the system. At the base, you can see the spigots, which will be the connectors to the tubing. They're positioned at the base to try to prevent any form of bubble formation within the tubing, as well as keeping pressure level between the two tanks so that the medium can naturally pass from one tank to the other without a separate pump to do that. In the center, you can see my pressure modulator, which functions by having the tubing running along the small trough that can be seen in the center, and a small servo or step motor will be turning the wheel on the right. The turning of the wheel on the right will cause the central arm to be moving up and down, which will compress and release the tubing, thus decreasing and increasing the diameter of it on the tail end of the perfusion chamber. Due to the nature of our peristaltic pump that we will be using, the pressure on the front end will be consistently maintained. So by modulating the outer diameter of the tubing, the pressure inside the system can be modulated up and down to better stimulate in vivo conditions. Here is the diagram once again, so that you can get a little bit of a bearing on where these systems are. So the medium tanks, as you can see, have the solenoid in between them, as well as on an exit pathway. This will allow them to be switched when you're emptying the tanks or re-switched when medium flow can be resumed to the normal pathway. The medium will flow from the tank over into the oxygen exchange, which will then flow into the peristaltic pump where pressure will be maintained. From there on, you can see it moves upwards into the perfusion chambers and then downwards into the cyclical pressure module. In between these systems are a series of dissolved oxygen sensors, which you can see. Those will be used to track cell proliferation to get an idea of how well the cells are doing without interrupting anything. here is the design for the actual perfusion chamber. So on the top left, you can see my SolidWorks designs, and then on the right, you can see the fabricated models made on a form-free resin printer. The first design, which is the topmost left, was designed mainly with the central geometry in mind, and the outer geometry wasn't acknowledged as much as I wish I should have. As you can see, there's not much force keeping the cap aligned to the base, as well as no effective way to attach it to the actual bioreactor. These issues were addressed in my second model, which is now a little bit bigger. It's held down by bolts to create a lot more force, which will compress that gasket and create a far better seal. The internal geometry between the two was not changed, however. Also, the second model will be far easier to mount to the actual bioreactor. As you can see in the bottom left photo, it can be put onto a bracket easily, and that bracket can be 3D printed or even cut from any kind of biocompatible plastics or easily sterilizable plastics. Inside the bioreactor chamber is the perfusion cassette. This is a personal design that I wanted to incorporate more customizability into the bioreactor. So on the left, you can see a cylindrical design. This one is meant to operate with taller, more cylindrical designed scaffolds. So this will work well with studies that are working on porosity, as well as the release of drugs on different aspects or different parts of their scaffold. Moving to the right from the left, you can see the mesh design, which is designed to work with a fine mesh that will be laid over the bigger blocky kind of grid you can see. This is meant to operate with harder scaffolds like ceramic beads or perhaps even ceramic fragments where you would seed osteocytes or other hard cell types. Moving onwards, you can see the cupped design, which is the typical standard in my mind. It has a tapered wall design so that it can create a tighter seal at the base, allowing the medium to flow through the entire scaffold, as well as a simple radial hole design to allow for minimal loss of scaffolding while maximum flow of medium. On the right, you can see a square design, which is meant to highlight the customizability of the cassette design, allowing you to better customize the internal geometry to the scaffold that you have. That way, the seal can be made to be just as good with any form of shape or size scaffold, allowing the bioreactor to be used in more experiments and expand the viability of the device. Here are some of the purchased subassemblies that are used in the bioreactor. You can see our peristaltic pump is a Masterflex brand. It has 2 channels and 6 rollers, and it will allow us to maintain a constant pressure and a constant flow rate, which is vital to keeping the cells alive, happy, and healthy. The pinch valve will be used with the medium tanks, as you saw before, allowing us to cut off the connection between the 2 tanks, allowing us to drain the waste tank while maintaining the primary tank's flow. Then they can be reopened and more medium can be introduced to the system, allowing the system to continue without having to be paused or interrupted in any way. The tubing will be mainly the platinum cured silicone tubing, but as well as some Pharmed tubing for the rest of the system. This was chosen for its non-permeability as well as its ease of sterilizable. Here are some of my acknowledgements and some of my references, as well as the diagram once again, if you would like to see where the positioning of the individual components are. Moving onward, I have been using computational fluid dynamics to analyze the design of my perfusion chamber. And with those results, hopefully I will be able to optimize it as well as correct any mistakes that I've made or any issues that were just simply unforeseen.